Welcome all. Today we will start with the buckling analysis. Last time we saw the static buckling analysis, and today we will be looking into the theory of dynamic buckling. So, let us start the course. So, theory of dynamic buckling. So, what is the difference between the dynamic buckling and the static buckling? Okay. So, the difference is as follows. Okay. Unlike the static buckling that concerns the steady state loads, okay, dynamic buckling involves suddenly applied loads that can greatly affect static Euler loads without causing immediate large deflections. Okay. So, in the first case we were dealing with the steady loads. Okay. Now, we will be dealing with the suddenly applied loads, okay, impact loads or the blast loads, okay, that are considered as the suddenly applied loads. Okay. So, in dynamic buckling what we do is that instead of finding the maximum load a bar can carry, dynamic buckling focuses on specifying a load and analyzing how buckling grows with time under this load. Okay. So, understand this thing. Okay. A static load is a load applied like this. Okay. So, what we normally do? We normally start with a loading. Okay. So, let us say we consider the loading as a static loading. Okay. So, in principle there cannot be any static loading. Okay. There will be always a change with respect to the time. Okay. So, when we analyze the deflection, okay, or the response of the system with respect to the time, what we see is that there are two components to the response. Okay. One is the steady state response and one is the transient response. Okay. So, that is the total response of the system. Okay. And if we look over a great period of time, okay, what we will see is that due to the damping and other effects, okay, the transient effects die down. Okay. So, only thing that remains is the steady state solution. Okay. So, this steady state solution we approximate as the static solution. Okay. So, in the static solution we also assume that the effect of the inertia is also not engaged. Okay. So, these are called the steady loadings. Okay. In dynamic loading the effect of the transient effects are present for a longer duration of the time. Okay. So, what we do is that in the static case of buckling, okay, in the static case of buckling like a bar, okay, so we take a particular applied load, okay, and we try to see, okay, what is the value, okay, that will cause the buckling in this system. Okay. So, under static condition we try to estimate the load that will cause the buckling. Okay. But in the dynamic case what we do is that we do not focus on the magnitude of the loading. Okay. What we do is that we specify the growth of the buckling, okay, under any given loading condition. Okay. So, as the loading condition is varying with respect to time, how the buckling will emerge, okay, or how it is going to propagate in the system. Okay. So, this is the difference between the static buckling load and the dynamic buckling analysis. Okay. So, let us look into an example scenario. Okay. A bar, we take a bar that is supported laterally along its entire length and it is suddenly released from a constraint at time t equals to 0. Okay. It means that there is an initial disturbance caused in the bar. Okay. So, this disturbance initiates buckling under a high axial compressive load P, okay, much larger than the static Euler load PCR. Okay. So, let us look into the governing equation. Okay. So, earlier remember what we used to do. Okay. Earlier we took only the component due to the stiffness component, okay, and we took the loading combination. Okay. Now, since we are considering the dynamic load, we are also considering the inertial effect. Okay. So, the lateral displacement of the bar is governed by the partial differential equations. Okay. This thing we have already covered earlier. Okay. So, if we go back into our approximation of the bar. Okay. So, remember we started with this bar. Okay. We started with this bar. Okay. So, we started with a bar, okay, and axial loads are being applied. Okay. And then we were looking into the vertical deflection of the bar, okay, from the unsteady initial deflection point. Okay. So, y was taken from the static equilibrium position. Okay. After that what we did was we took out a differential element, okay, we cut a chunk of element, okay, we cut a chunk of the differential element out here, okay, and then we applied the equilibrium conditions. Okay. We applied the equilibrium conditions. Okay. So, the inertial forces will be acting on the system. Okay. The change in momentum occurring due to the length will be occurring. Okay. So, after that we wrote down the governing equilibrium equations. Okay. So, the summation of forces in the vertical y direction. So, in the vertical y direction we have shear forces, okay, going in this direction and shear forces going in this direction. Okay. So, the two shear components, okay, plus the mass component, okay, the inertial component. Okay. So, this is the summation of the forces in the vertical y direction, okay, or in the differential form this is the solution. Okay. After that we wrote down the moment equilibrium about point B. Okay. Here we are neglecting the effect of the rotary inertia. Okay. So, moment is acting like this, okay, it is acting in this way, this fashion. Okay. So, these two components of moment comes out to be here. Okay. After that the component we are taking moment about this point. Okay. So, the shear component will act here. So, the shear component is written down out here, okay, and the component due to the axial force, okay, and this component due to the axial force. Okay. So, this is causing a moment about this distance. Okay. So, we wrote down all the components and we reduced this equation. Okay. So, here we neglected the higher order terms. Okay. After that we assumed the Euler-Bernoulli beam. Okay. We made an approximation that we are considering the Euler-Bernoulli beam by making an approximation of the curvature. Okay. So, after doing all the force and moment equilibrium, okay, we got the differential equation. Okay. So, this is the differential equation governing the dynamic elastic buckling of a simply supported bar under compressive axial load. Okay. So, after that we ignored the inertial terms, okay, and we did this problem as a static buckling case. Okay. So, now we are introducing the inertial component, okay, and we are now going to solve this thing as a dynamic elastic buckling problem. Okay. Okay. So, here is the partial differential equation. Okay. The same equation, earlier we ignored the inertial component, okay, now we are introducing the inertial component because now we are dealing with the dynamic buckling equation. Okay. Rho is the material density, okay, A is the cross sectional area, E is the Young's modulus, I is the second moment of area, P is the compressive axial load and X is the axial coordinate at time t. Okay. So, this is our beam, okay, and axial load P is being applied, okay, and W is calculated from the static equilibrium position. Okay. So, now let us try to solve the governing differential equations. So, now what we are trying to do is that we are introducing some normalizing variables. Okay. So, alpha, eta, c and tau. Okay. C we have already seen, this is the velocity term. Okay. So, alpha resembles normalized load. Okay. So, alpha is resembling our normalized load, eta is related to inertial component, okay. C is the axial wave speed, okay, the velocity component, and tau is the dimensionless time. Okay. So, now introducing these parameters, okay, into the parent differential equation, into this equation, okay, let us call this equation 1 and all the parameters as 2. Okay. So, when we put back 2 in equation 1, we reduce the equation to this form. Okay. So, this equation should satisfy the boundary conditions. Okay. So, at the boundary condition we introduce the terms, okay, the deflection at the two boundaries, okay, at time t equals to 0, at time t equals to t, okay, at the ends is 0. Okay. So, at this end x equals to 0 and at this end x equals to 0, the vertical deflection is 0. Okay. Okay. And after that we introduce the rotational component. Okay. So, at the two ends, okay, this term 0 displacement and 0 bending moment at the supports. Okay. So, displacement is 0 and this term is giving the bending moment. Okay. So, this term at two ends, okay, this term at two ends will be 0, the bending moment at this end is 0 and the bending moment at this end is 0. Okay. So, we are putting these two terms as 0. Okay. So, at any given time t, the deflection at two ends and the bending moment at two ends will be 0. Okay. So, these are the boundary conditions that we are going to use. Okay. So, after that what we are trying to do is that we are expressing the lateral displacement as a Fourier series. Okay. We are expressing the lateral displacement as a Fourier series. Okay. So, we are using a sine series approximation. Okay. So, the initial displacement imperfections can also be expanded. Okay. So, we are also introducing the term for the initial displacements or imperfections. Okay. So, coefficient ANN is calculated by the orthogonality integrals. Okay. So, once we have done all this thing, okay, so the equation of motion, okay, we can decouple this thing, okay, using the orthogonality, modal orthogonality, and the decoupled equations of motion for different modes are given by this term, okay, where omega n is giving us the frequency of the system. Okay. So, the nature of the solution will depend upon the sign of omega n. If omega n is greater than 0, the solutions are bounded oscillations. Okay. If omega n is less than 0, the solution will grow exponentially, indicating buckling instability. Okay. So, if omega n is less than 0, there will be a buckling instability in the system. Okay. Otherwise, the system will be oscillating. Okay. Okay. So, the critical mode number. Okay. So, there exists a critical mode number NC separating stable and unstable mode. Okay. So, there will be a critical mode number, okay, which will separate the stable and unstable modes. Okay. So, modes with n less than NC become unstable and grow exponentially, manifesting as the buckling modes. Okay. So, this instability is treated as the buckling modes. Okay. So, now we will try to relate this dynamic instability with the static buckling. Okay. So, the wavelength corresponding to the critical mode NC matches the classical Euler buckling wavelength. Okay. So, there is a relationship between the NC and the Euler buckling wavelength. Okay. If this is the Euler buckling wavelength, this is the relationship between the two. Okay. So, the dynamic analysis generalizes static buckling results, okay, allowing for load magnitude beyond static critical load. Okay. So, here we can also look into the load magnitude beyond the static critical loading. Okay. So, now again we are introducing some of the dimensionless formulation for the scaling purposes. In the space coordinate, we are scaling it with zeta. Okay. Zeta is nothing but the relationship between the length at any point to the total length. Okay. So, x over L becomes my zeta, and the time variable, okay, any time t with respect to a characteristic time t scale related to wave speed and bar properties. Okay. So, this is the time, okay. This is called a characteristic time which relates to the wave speed and the bar properties. Okay. So, we have scaled the length also, we have scaled the time also. Okay. So, we have introduced two terms which are giving the dimensionless quantities in terms of time and space. Okay. So, now we will normalize the lateral deflection also. So, lateral deflections we are normalizing by the use of radius of gyration. Okay. So, ratio of the buckling wavelength scale to the radius of gyration gives dimensionless parameter controlling the buckling behavior. Okay. So, this ratio is giving us the dimensional parameter which is responsible for my buckling behavior. Okay. So, initial conditions and the final solutions. Okay. So, bar is initially at rest with an imperfection shape W naught. Okay. So, this is the W naught imperfection shape. Okay. So, this is the initial position of the bar. Okay. And then an initial lateral velocity and displacement are the known quantities. Okay. So, now we look into the generalized solution. Okay. So, final time dependent solution is expressed as a sum over modes. Okay. So, the final time dependent solution is expressed as a sum of the modes involving the modes will have different features. Okay. So, it will have hyperbolic functions for unstable buckling modes. Okay. If there are unstable buckling modes, okay, so it will be given by an hyperbolic functions. Okay. And if there are stable modes, it will be given by a trigonometric functions. Okay. And the amplitudes are determined by the initial conditions and the mode stability. Okay, how much this amplitude is there, it will be dependent upon the initial conditions and the stability involving the modes. Okay. So, what are the physical implications? Okay. So, the dynamic amplification and the buckling growth. Okay. Modes with exponential growth dominate buckling behavior. Okay. So, the modes which are causing the exponential growth, okay, they are dominating the total buckling behavior. Initial imperfections are amplified dynamic. Okay. So, whatever initial imperfections are present, okay, they will be amplified. Okay, their effect will be amplified by this dynamic nature of the behaving system. Okay. The length of the bar may become unimportant for short wavelength high modes due to the rapid growth and localized buckling. Okay. So, the effect of the length of the total bar, okay, this effect, okay, will have less significance, okay, due to the short wavelength and high modes, okay, because the localized buckling, okay, the growth of the localized buckling is very rapid. Okay. So, it does not matter what is the effect of the length of the bar. Okay. Now, the application of these things for the impact loading. Okay. This theory models impact or sudden loading scenario. Okay. This theory is able to model the impact or sudden loading scenarios where axial stresses are much higher than the static buckling load. Okay. The axial stresses effect, okay, they are of higher magnitude than the static buckling load. Okay. This explains the observed phenomena such as multiple small wavelength buckles forming rapidly near the impact zones. Okay. As we have seen near the impact zones, this type of multiple buckling shapes are occurring. Okay. So, this analysis is able to explain this type of behavior, the dynamic buckling behavior. Okay. The physical meaning. Okay. The amplification function is often written as Qn, okay, the modal part, okay, which we have seen here, okay, the modal amplitude part. Okay. So, Q is giving me the modal amplitude part, okay, and instead of T, okay, instead of T we are using tau as the dimensionless time. Okay. So, the effect of the modal amplitude, okay, at a dimensionless parameter, okay, this will dominate the amplification function. Okay. So, this is the amplification function. An will come from the solution of the Fourier series. Okay. Okay. So, here the initial displacement imperfections, okay, this quantity An, okay, it will also be a part of the amplification function. Okay. So, the amplification functions will have two parts, one is the mode amplitude and other is the coefficient due to the imperfections. Okay. So, this is the solution for this part. Okay. Okay. So, here it can be written in this form also. Okay. So, the amplification function measures how much the amplitude of the nth mode. Okay. Qn is called the nth mode. Okay. So, any mode, okay, so it gives us a measure of how much the amplitude of the nth mode, Fourier mode or wavelength number k, grows relative to its initial magnitude as a function of dimensionless time. Tau is the dimensionless time that we are dealing with and the axial load alpha. Okay. Here hyperbolic sign indicates exponential growth for unstable buckling mode. Okay. So, here we are dealing with the hyperbolic functions, it means that we are dealing with the unstable buckling modes. Okay. So, the amplification function is relating the Fourier mode, okay, Fourier mode relative to its initial magnitude, okay, and this is given by an dimensionless time and the axial load. Okay. So, the most amplified mode, which mode will be most amplified? Okay. So, as the time increases, okay, tau becomes large, okay, only modes with the large amplification, with the largest amplification, that is the most amplified or the preferred mode, dominate the response. Okay. With the increase in time tau, okay, only modes with the largest amplification, the modes which are undergoing the largest amplification will dominate the entire response, or they will become the preferred mode. Okay. So, this mode can be found by the maximizing the amplification function with respect to the wave number. Okay. So, what we need to do is that this is the amplification function. Okay. This is the equation for the amplification function, and it is related with the wave number k. Okay. So, what we need to do is that we need to differentiate this amplification function with respect to the wave number. Okay. And that will give us the differentiating the amplification function with respect to the k and setting the derivative to 0 and solving for k equals to k star, it will give us the dominating mode. Okay. So, for large time tau, the hyperbolic sine grows rapidly and the peak gets sharper, approaching the value where the exponential growth rate is the highest. Okay. So, for large tau, the locus of the most amplified mode is approximately given by this function. Okay. So, this is an approximate solution, and more precise estimates include small corrections in terms of tau. Okay. So, if we write down k star, okay, approximately equals to root over alpha. Okay. So, this will give me the most amplified mode. Okay. And alpha we have already seen. Okay. So, alpha was the normalized load. Okay. So, the most amplified mode, okay, will depend upon the normalized loading condition. Okay. So, it depends upon the alpha. Okay. So, the wavelength of the most amplified mode. Okay. So, similarly, we can calculate the wavelength of the most amplified mode. So, wavelength lambda equals to twice pi over k. So, the most preferred mode k star, we can calculate the wavelength of the most preferred mode. Okay. So, for very high axial loads, okay, it means that if alpha is very large, the preferred mode number and the wavelength decreases. Okay. That is, buckling occurs at the shorter wavelength. Okay. Okay. So, here we can see, okay, we have the expression for alpha PL square over EI. Okay. So, if we put the values here, okay, we try to put the value here. Okay. So, k star will become root over PL square over EI, okay, roughly equal to PL square over EI. Okay. Means k star becomes a function of root over P. Okay. So, k star is related directly to the applied loading. Okay. So, again the k star, okay, k star is related to the, so as the load becomes higher, okay, as the load becomes higher, okay. So, for very high axial loads, okay, k star is related to my root over P. Okay. So, as k approaches root over P, okay, that is for a very high load, okay, for very high axial load, the preferred mode number and the wavelength decreases. Okay. The wavelength, okay, is inversely proportional to 1 over k star. So, as k star is dependent upon root over P, so as P goes higher, my wavelength will decreases. Okay. So, it means that the buckling is going to occur at short wavelength. Okay. So, the physical interpretation and the evolution. Okay. So, narrowing of the amplitude modes. Okay. So, as the dimensionless time grows, okay, a narrowing band of wave numbers modes around k grows fastest. Okay. The amplification function becomes sharply peaked, okay, meaning that nearly all visible buckling will concentrate near the preferred mode. Okay. So, what is happening here is that as the time becomes larger, okay, as the time becomes larger, the hyperbolic sine function, okay, it is going to grow rapidly, okay, and the peak goes sharper and sharper. Okay. So, this will occur at the values where the exponential growth rate is the highest. Okay. So, for the large time, okay, as the time t grows large, okay, a narrowing band of wave numbers will occur around k star. Okay. So, the preferred amplification will occur around the value of k star. Okay. So, the amplification function becomes sharply peaked. It means that all visible buckling modes will concentrate near the preferred mode. Okay. So, k star is the near the preferred mode. So, all visible buckling modes are going to form out here. Okay. Let us say for tau greater than 5. So, at this stage the amplification is so strong that plasticity or the nonlinear effect will set in. Okay. So, this becomes a critical threshold for design. Okay. So, this dimensionless time quantity, okay, when it approaches, it is greater than or more than 5. Okay. So, this is a critical value for the threshold for the design purpose. The load amplitude and duration, the combination of the axial load, okay, alpha is related to PL square over EI. Bar characteristics, okay, that is the stiffness and the inertia, and loading time tau governs the total impulse delivered. Okay. So, the total impulse occurring in the system will be a function of all these parameters. Okay. So, at the onset of the pulse buckling, okay, significant exponential growth of any mode can be predicted by tracking when the amplification function first becomes much larger than 1 for some k. Okay. So, in this particular case, if this guy is becoming more than 1 or k star is becoming then more than 1, then the first mode is going to onset. Okay. Okay. So, the amplification mode is becoming larger for some k. Okay. So, here we have dealt with the dynamic buckling. We started with the equation of motion for the dynamic buckling case, the differential equations. Okay. We tried to solve it and we tried to see how the dynamic amplification function is related to the modes, how the modes are going to propagate, and what is the condition at which the maximum value of the dynamic buckling is going to be formulated and how it is going to propagate into the system. So, today I will stop here. Thank you.